Good evening, all. I am doing a test to see how this works. This is a different program than what I'm used to using, and I hope this finds you well. Today we are going to be talking about how to prove conjecture through deductive reasoning. Now, for those who don't know or don't remember, conjecture is a testable statement that is based in a series of facts. The issue, of course, is conjecture really hasn't been 100% proven at all points. I often use the example of evolution, not because I don't believe in it, but it's a good example of conjecture. We know it fits the evidence, but because we lack a full fossil record, it's not 100% impossible to disprove. All right, well, we'll take a look at your notes, and we see the first line of the page talks about conclusions. When you're in the lab for the chemistry or bio or physics, the last thing in your lab report usually talks about a conclusion. Generally, our conclusions are based on what we observe in the lab, or you could say on what we know to be true. And in fact, that is what we find. Conclusions are generally based on a series of statements that we accept are true. And if we do that, we call that deductive reasoning. So if I take a look at our first example here, we are given a set of statements that I think most of us can agree on. So if we take a look here, weightlifting builds muscle. That's generally a true statement. Muscle makes you strong. Another relatively true statement. And finally, strength improves balance. Generally, we can find that as relatively true. And now, once we've read that, we have what's left is Inez lifts weights. What can we then deduce about Inez? Well, if we think of Inez as a weightlifter, generally we can probably say that Inez is, and I'm going to put a colon there, Inez is usually could be probably these things. Inez is probably building muscle. Okay, and we can say that because that statement right here tells us so, right? Inez is working out and therefore is probably building muscle. What else is true? Well, we find that probably Inez is fairly strong. And we can tell that because right here it says muscles make you strong. And if Inez is building muscles, I can assume that she's probably going to be fairly strong. And lastly, we can kind of prove that she's probably going to have good balance. Probably has good balance. And we can say that because we all agreed on the statement that strength improves balance. So just by looking at that statement and breaking it down, we're able to deduce some things about Inez that are probably and most likely true. Okay, so if we work together, we have to change this into some math. So if we work together, we're going to kind of create some true statements about math. Okay, and in math, we talk about even numbers, and everyone knows what an even number is, right? Of course, it's going to be 2, 4, 6, 8, so blah, 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 so on and so forth. But how do we show that algebraically? Well, if we let x equal a number, okay, right away there's a 50-50 shot that it's going to be odd, which means it's not even. So we have to create a clever way to kind of ensure we're going to have an odd or an even number, pardon me. And we do that by simply saying that any even number right there is going to be divisible by 2. Okay? So, divisible by 2. All right? And a sneaky way to make sure any number is divisible by 2 means we can multiply it by 2. So, a true statement would be that 2x, okay, or any combination of variables and coefficients will always be even. Okay, so if I put any number and multiply it by 2, it will always be even. Okay, and if let's give you a chance. I plug any number into 2x and see if it becomes odd. I guarantee you it won't. Okay, well, now we have to define an odd number. So if x is any integer, once again, we still have this problem where there's a 50-50 shot of it not being odd, where it could be even. Well, do we have a way to guarantee something is going to be even? We do. Well, we can multiply something by 2. Right? If we multiply any number by 2, it is going to be an even number. Well, how do I get to odd? Well, I can add an odd number to it, right? Well, the simplest odd number that we can add is 1. So in effect, what we can do is say that 2x plus 1 will always be odd. All right? So if I plug 2 in there, right, 2 in for x, well, 2 times 2 is 4, plus 1 is 5. That's an odd number. Well, let's test an odd number. 2 times 3 is 6, plus 1 is 7. Well, that's always going to be true. If I multiply a number by 2, I'm going to get an even number. And if I add a simple odd number, it will always be odd. So that's the definition of an algebraic even number and an algebraic odd number. So we have right here, we have the even number, and I'm going to choose a different color here, and this is going to be the definition of an algebraic odd number. Okay, well, what we have next is, let's continue the English lecture. Okay, we have the word consecutive numbers. When we talk about consecutive numbers, we're usually talking about numbers that come one right after another. So an example of that would be 1, 2, 3, or 7, 8, 9. Those are all examples of consecutive numbers. And when we talk about consecutive numbers, because they're what we call related to each other, okay? Because they're related to one another, right? They are connected by a common thread. In effect, we only need one variable. Okay, and variable. Okay, so let's take a look. That means that x plus 1 and x plus 2 are 3 numbers that come after one another numerically. So let's plug any value in for x. I like saying let's just let x equal 2. Okay, let x equal 2. Okay, so if I put 2 in for x, I get 2 plus 2, or 2 is, the next one is going to be 2 plus 1 is 3. And 2 plus 2 is 4. Are those consecutive numbers? Well, they are. Okay, which kind of shows us that we're dealing with the right thing. Okay, let's kind of put your deductive reasoning skills to the test now. So I'm given 2x, 2x plus 2, and 2x plus 4. Okay? What does that mean? Well, if we take a look at it right here, and I should have picked my black color for that, but that's all right. 2x is what? Well, we define 2x as our definition of an even number, right here. So I'm going to have an even number plus 2, and an even number plus 4. Well, are they consecutive? Well, they're not 2, 3, 4. Instead, they're what we call consecutive even numbers. Okay, consecutive even numbers. So let's plug 2 in there. 2 times 2 is 4. Okay, 2 times 2 is 4 plus 2 is 6. And 2 times 2 is 4 plus 4 is 8. So 4, 6, and 8. They are consecutive as they are the next even number in the series, and that's why we're able to say they're consecutive even numbers. And how about the next one? If that last one wasn't a really good clue to you, that's okay. Let's take a look here. Well, I'm given my base number is 2x plus 1. Well, if we draw our line right here, that is the definition of an odd number. So 2x plus 1, 2x plus 3, and 2x plus 5. I'm still adding 2 more to every single one, so these ones are going to be consecutive odd numbers. And we can once again plug that 2 in. 2 times 2 is 4 plus 1 is 5. 2 times 2 is 4 plus 3 is 7. And 2 times 2 is 4 plus 5 is 9. 5, 7, and 9. They are consecutive odd numbers. All right? So let's try and put this into perspective of using an algebraic proof. And I always would say, as a physics teacher, it's probably the best idea to break something down. Let's break down the problem. Okay, let's pick out some key words in this sentence. Okay, so we're going to use deductive reasoning to prove that the product of 2 odd integers is always odd. Well, the key word in this sentence, one of the key words, is right here. Product. Okay, what does product mean? Well, we refer to it as a mathematical function meaning times. Okay, and I'm going to draw my little x. Okay, it's a times function. Okay, the next thing we have is 2. Okay, I have 2 different numbers. Are they related? To say consecutive anywhere in there? It doesn't. So what this tells me is I need to have 2 different variables. I need to have an x and a y. Okay. Now, what do I know about those variables? They are going to be odd integers, which means that they're going to have to follow this rule right here. They're going to have to be 2x plus 1. Okay, so they have to follow 2x plus 1. Okay. And lastly, the last thing on our list is that they are always going to be odd. And what that means for us is that my end result should look like 2 times some x plus 1. And I'm going to replace that x with a z just to say it could be any number. So that's what we should look like in the end, is 2 times z plus 1. That's, in the end, what it should look like. Are there any more details I can pull out of this question out of this statement? Really, there isn't. Okay, so let's start trying to do some math, okay? Well, I know I have to have x and a y. So I'm going to state, and I should always make a statement when we're dealing with proofs. I'm going to say let x and y represent any integer. Any integer, okay? And because of that, we can say, and I use this as a kind of bridge, that means therefore, okay? So therefore, 2x plus 1 and 2y plus 1 are odd. Okay, which is true. We need to have odd integers. Okay, so how do I put this into an equation, or I start working with this? I need to say, okay, I have a product of something, which means I'm multiplying those two terms together. So I get 2x plus 1, and I'm going to put my brackets up, and I'm going to multiply it by 2y plus 1. Okay, well now, I have nothing I can pull from the question. There's no more logic jumps I can make. All that's left is the math. So can I algebraically multiply this out? Well, I can. Okay, so if I do my FOIL technique, this multiplied by this, and this multiplied by this, followed by this multiplied by this, and this multiplied by this. Okay, and what that gives me is 4xy plus 2x plus 2y plus 1. Okay, and if I'm looking at that, and all of you know you're supposed to give things in its simplest form, I have no like terms I can combine. There's none, right? I have xy, I have x, and I have y, and I have a constant. Really limited on what I can do. But I can take a look, is there a common factor in any of that? And I know many of you are probably going to say, well, I really want to pull a 2 out, but this last term right here doesn't have a 2 in it. Well, that's okay. Well, let's simplify it, and let's just say we'll take this, and we can pull a 2 out of here. So when we do that, we get 2 times 2xy plus x plus y. And I'm going to leave that 1 alone. Okay, so it's starting to look familiar. Is there a way I can substitute or take out this term, algebraically to make it look even more like I want? Well, I can. I can replace that with an entirely new variable. I could say 2 times z plus 1, okay, where z is equal to 2xy plus x plus y. Are these two things the same, or at least similar? They are. So I have mathematically proven, because this is guaranteed to be odd, and this is going to be odd. So therefore, every time I multiply two odd integers together, regardless of what they are going to be odd. The product is going to be odd. Okay, so when we start talking about getting close to the end of a proof, all right, we have to talk about what it should look like. And in essence, when we're looking for trying to prove something that should be even, in the end, it should look like 2 bracket some value, okay, So 2 times some value. It could be any value, but if we can pull a 2 out, we know it's going to be even. Okay? And that's how we could prove that something is going to be an even number. Same thing with an odd number. If we're trying to prove something is going to be an odd number, it should look like, in the end, 2 times some value plus 1. Okay? And that's always guaranteed to give us an odd number. And lastly, if we're looking to have something divisible by 3, deductive reasoning would suggest, like an even number is going to be divisible by 2, a number that's going to be divisible by 3 should probably start with a 3 times some value. And we could continue that on forever and ever. If I want to say something's divisible by 4, something's divisible by 5, 6, 7, so on and so forth, it needs to be able to have a 5 pulled out somewhere with no trail to it. Right? We'll see that there's nothing after that 2. It's simply all contained within the brackets. All right? Let's take a look at some actual practice problems. Okay, so using deductive reasoning to prove the difference between consecutive perfect squares is always an odd number. Let's stop. Let's break this down. What's the key words? So I'm looking at this, and the first key word I see is difference. And when I hear the word difference, the first thought that comes to my mind is a function. Okay, it's got to be one of the big 4 functions: multiplication, division, addition, subtraction. Well, when we talk about division, difference, we are talking about a subtraction of some sort. Okay, so we are dealing with a subtraction just from reading the problem. The next keyword I see is consecutive. Okay, and if I'm dealing with consecutive, I should know, looking back at my definitions, I'm going to be dealing with one variable. One variable. And personally, you can pick any letter you like. I'm going to stick with X because that's the one I'm most comfortable with. So we're going to have some X we're dealing with. Okay? And then the next thing I see is perfect squares. So that means at some point in time, I'm going to have to make sure that I have some, and I'm going to replace that with Z squared. Okay, and I'm going to use my caret, Z squared. I'm going to have to square that function eventually. All right, and the last thing that's in this question is an odd number, which means what? Well, that means that my answer should probably look like 2 times some value plus 1. So that's what our goal is right there. And oftentimes that kind of helps people get directed in this stuff. So if you know what your goal is, you can kind of work backwards to get there if you need to. Okay, so we're going to start with our statement. So I'm going to say let X equal or represent any integer. Okay? And therefore, and I'm going to draw my little therefore symbol, therefore, okay, X plus 1 is the next number in the series. Which makes sense, right? If I had put a 2 in there, the next number in the series is going to be 3. Perfectly flawless. Okay? So, is there anything else I can write down? Is there anything else I can pull from that equation? No. We've pretty much got everything. Okay, so now we have to make some decisions. I have this difference function right here. And difference means I have to subtract. Is it easier for me to subtract the small number from the big number or the big number from the small number? Well, it's usually easier to subtract the small number from the big number. Which one's the smaller number? Well, it's going to be X because X plus 1 is bigger. Okay, so if I take a look at this, I'm going to put X, subtract 1, or for x plus 1, subtract x. But remember, right here, it says I have to look at the difference of perfect squares. So I'm going to have to make sure that both of those values are squared. Okay? So I'm left with x plus 1 squared, subtract x squared. And I'm aiming for something to be 2 something plus 1. Okay? Nothing more I can do. Can I multiply and expand this out? I can. So if I take x plus 1 and square it, what I'm going to get is x squared plus 2x plus 1, and that's subtract x squared. Okay? So, is there anything there I can cancel out? Well, x squared and x squared. And that leaves me with 2x subtract 1. Or sorry, 2x plus 1, pardon me. Wait a minute. This and this look the same. Therefore, we can say that any time I take the difference of two perfect squares, it's going to be an odd number because that's the definition of an odd number. Okay? So if I use deductive reasoning to prove the sum of an odd number and an even number is always odd, breaking this down, we'll do this real quick. Okay? Prove the sum is an important number of an odd number and an even number is always odd. So, right from the question, I know I'm dealing with a plus, because I'm summing something. I have an odd number, which means I'm going to have my 2x plus 1. I have an even number, which means I have my 2x. And I'm going to have my proof trying to prove that it's going to be 2x plus 1 somewhere down the line. Okay? So, like always, let's start with a statement. Let x. Okay? Well, and we have to decide, are these two numbers related? They're not. So therefore, I need two variables, x and y. So I say let x and y equal any number. And I can also say that 2x plus 1 is odd and 2y is even. Those are two true statements right there. Okay? And if I say that, then we can take a look and let's start mathematically this out. The sum of them, I'm going to have bracket 2x plus 1, bracket plus 2y. There's nothing more I can do there. So let's see if we can kind of rearrange this to get things together. I can move that y around, so it's 2x plus 2y plus 1. And if I do that, we can see that I have a common factor here, and that's that 2. So I'll get 2 times x plus y plus 1. And guess what? That's the definition of an odd number. So we've just proved that anytime I add an odd number and an even number, I will get an odd number. So, next question is prove the square of an even integer is always odd. Breaking this down, I have this square function. I know I'm starting with an even integer, and I'm always trying to show that it's even in the end. Okay, so how many variables am I dealing with? Well, I'm only dealing with one variable because I'm only dealing with one even number. Okay, so I'm going to deal with an x. And of course, I'm going to say let x equal any number. Okay, and by doing that, I can say 2x is equal to an even number, which is true. All right, so now I can go down and say, okay, I'm squaring that, so I have 2x and I'm going to bracket that, and I have to square the whole thing. I have to square. Well, if I multiply that out, 2x times 2x is going to give me 4x squared. Well, that's not right away something I'm familiar with. Is there a common factor? Well, I can take a 2 out because I want an even number, and an even number is always going to be multiplied by 2. So that gives me 2 times 2x squared. Okay, and because I have that 2 out in front, that's going to tell me that no matter what number I put into the x, it's going to be an even number. Okay, so we've just proved mathematically that if I square any even integer, it is going to be an even number. All right, well, let's take a look at the next problem here. I'm trying to prove something. This is the trick you can see on Facebook or on TikTok, where someone kind of tells you to choose a number. They do a series of math, and it comes back out to the number you left with. Okay, or you know, do the number you were thinking of, something. So let's disprove this mathematically. All right. Well, let's read. Okay, we're going to start with a number. Well, algebraically, if we're trying to start with any number, well, we might as well represent that by putting an x. Okay, so x is going to be our number. Step 2 is we're going to have x, and we're going to add 2, x plus 2. Okay, then we're going to multiply the whole thing by 3. Okay, so if I multiply it by 3, I'm going to have 3 times x plus 2. And if I do that, I have to multiply it into everything. So that leaves me with 3x plus 6. Well, the next step is I'm subtracting 6. So if I get rid of that 6, I'm left with 3x. Okay, and if I subtract my original number, 3x subtract x is going to leave me with, you guessed it, 2x. And my last step is I have to divide by 2, and if I take 2x and divide by 2, I get left with, you guessed it, x. So our last, we've just proved that no matter what number I choose, this will work. Okay, and the last example we have for you, this is the hard one. People struggled with this, and I don't. It's a little bit more complex in the wording of it. Okay, so let's break it down exactly like we always do. So I have the sum of something, which means I'm adding. Okay, and I have a 2-digit number. Well, how do I represent a 2-digit number? Well, does the tens place and the ones place have to be the same? They don't. So I'm going to need 2 variables there, and I'm going to have to guarantee one is always in the tens place and one is always in the ones place. Well, I can represent that by saying x. Okay, we'll say x and y are my 2 variables, and I can guarantee one's going to be 10 by putting a 10 in front of it. Okay, 10x plus y. Okay, and I'll show you that over here. So I can write that as 10x plus y. Okay, it's the same as saying we'll place x as 2, right? 2 times x is 20, and we'll say y is 3. That's the same as saying 23. Okay, so that's what that really means, is we're going to represent by looking at something like this. And then the next statement is the reversal. Okay, is a multiple of 11. What's the reversal? What does that mean? So that means if I flip the 2 numbers, well, can we think of some numbers that are reversals of each other? Well, the prime example you can give is 23 and 32. Okay, We flip the two of them. Same thing if I said 45 and 54. Those are reversals of each other because we flip where the ones and tens places are. Okay? And the last thing it says is going to be a multiple of 11. And what that means is at the end, I should have something that looks like this. Okay? So, I'm going to say let x and y equal any number. Any number. Can be anything. Okay? Where 10 times something is in the tens place. Okay? It's in the tens place. Very simple. Okay? So, now I have to write this out mathematically. So I'm going to say 10x plus y. And I'm going to bracket all of that. And I'm summing, remember? So I'm going to have plus. Now I have to add the reversal, which is instead going to be 10y plus x. Okay? So let's do a check. Is there anything else I can pull from that equation or from that statement? There isn't. Let's take a look. Is there anything else I can do to make any statements? There isn't. All right, let's do some math. Are there any factors in the brackets I can add? Here or here? There aren't. So can I drop the brackets and try and combine like terms? I can. So let's do that. I'm left with 11x plus 11y. And my goodness, what we see is that that is 11 times x plus y. Okay, so in fact, if I reverse any two numbers, they're going to be multiples of 11. So if I take my 23 and my 32, 23 and 32 is 55. Okay, if I add 45 and 54, guess what? That's 99. 50, 55, and 99 are both multiples of 11. Boom. We've just proved mathematically that it works. Okay? So that is what we're talking about when we're talking about deductive reasoning. We're trying to show algebraically how to solve anything that comes out. We're usually given the answer whether we actually know it or not. Okay? So that's what we're looking for, and I hope this is helpful to kind of slow things down. You can stop where you need to, and maybe can give you a little bit of direction if you were lacking some of this. All right? Have a good evening, everyone.